The question I had posed in the previous video was, could we use our geometric series formula for this question? And at the time that I ended the previous video, I kind of left it on a cliffhanger as if to say we couldn't because we have some limitations here. And I'm going to use the existing problem that we have in letter A from number 5 as kind of a jumping off point, because I want to make sure we understand what parts of this geometric formula we can use and what parts we can't use, in the hopes that we can understand why we never used this formula in the first place. The reason why I did that little experiment with the pieces of paper was because there was something impossible about this formula at first. So just to make sure I remember, the formula that we referred to in the previous lesson was a sub 1 times 1 minus r to the n over 1 minus r, where a sub 1 is the first term in the series, r is the multiplier of the series, and n is the number of terms. So just to clarify, if I was doing the original series of little tiny post-its, the first post-it that I tried to add, the first post-it that I cut apart and tried to stick back together was the post-it for 1/2. So my first term was 1/2. The multiplier is what I was trying to cut each time. I was trying to cut halves each time, so the multiplier was also a half. N is the issue though, because n is the number of terms that I was trying to add up. Well, I had an infinite series of terms that I was trying to add up. So n isn't really a number. But picture a really, really, really big number, like 1,000,000. Picture 1,000,000 little cuts of that piece of paper. Or if we were into like really deep technology where we could really like be practically splicing atoms, maybe 1,000,000,000,000 or something really crazy. So I'll just keep making that an obnoxiously big number. Let's see what would happen if I plug in those values into my formula that I claimed I couldn't really use. If I plugged into the formula, I'd have a sub 1, that's 1/2, times 1 minus r, which is 1/2, to the power of n, which is infinity, over 1 minus r again, which is 1/2. Now, obviously, this can't be done. I didn't use this formula because 1/2 to the power of infinity doesn't really make any sense. It doesn't really have a possible value. Like if I pulled out my calculator, even a fancy calculator, it doesn't have an infinity button. I don't have a number to plug in for infinity. These calculators are actually kind of limited in what they can do. I can't even plug in a number that's very big. So let's imagine for a second that I was trying to plug in 1/2 to the power of something really big. Whoops. If I tried to do, say, 1/2 to the power of 1,000,000, so that's 6 zeros, the calculator is like, oh, that's 0. Well, it's not really. The calculator is actually estimating for us. The calculator is doing a little bit of trickeration, because what's happening is that the calculator is hitting scientific notation. I'll do 1/2 to the power of 100 to demonstrate this is scientific notation. This is 7.888 times 10 to the negative 31st power, which means 7.888, but you'd take that decimal and move it to the left 31 places. So you'd have 0.00000000000, 30 zeros, and then the 78886, etc. So by the time you start getting into really obnoxiously big numbers, like 1/2 to the power of 500, your calculator's like, oh, I'm sorry, I can't do that anymore. I don't have enough zeros to spare. And if you experiment this with a little bit of regularity, you can actually try to figure out what your calculator can handle. My calculator can do 1/2 to the power of 300, but it's running out of the ability to display. It's now at 10 to the negative 91st power, which is pretty tough. By the time I get to 10 to the 400, it's like, oh crap, I can't do that anymore. I'm just calling it 0. So notice how your calculator almost has the exact same attitude as I had when I was doing this post-it problem. You get to the point where you're like, oh my gosh, do you really need me to be this detailed anymore? Freaking crap. It's like nothing at this point. So even your calculator's like, holy hell, let's just stop right here. Let's just call it 0. Realistically, the answer is not 0. But it's probably got 0.000000000 with so many decimals that for all intents and purposes, it's basically 0 for all human needs, and the calculator's just like, oh, screw it. No, just fine. It's 0. And it's kind of cutting a corner. So if our calculator can't even do 1/2 to the power of 400 and get a very big number, imagine what 1/2 to the power of something really legitimately big is. Like 1 to the power of 1,000,000 again. Yeah, it's not happening. Add a few more zeros, it's definitely not happening. So by the time I start really getting into this crazy long infinity type situation where I might be adding so many fractions that we're splitting atoms at that point, even the calculator's like, it doesn't matter. That whole quantity is just going to be a 0. So notice then, if this yellow quantity that I'm highlighting is the part that in my calculator I'm basically getting such a ridiculously small number, it's for all intents and purposes 0. Notice what would happen to my formula then. I'd have 1/2 times 1 minus, this effectively comes out to be nothing, over 1 minus 1/2. Let's see what that would look like. 1 minus 0 in the parentheses is 1. So I have 1/2 times 1 over 1 minus 1/2. 1/2 times 1 is 1/2 over 1 minus 1/2 is 1/2. I have 1/2 divided by 1/2. You could do keep, change, flip if you want to, or you could just assume that 1/2 cancels 1/2. Or if you do keep, change, flip, the 2's cancel, the 1's cancel, you're left with 1. Now, that result might be a little bit surprising, because remember when we made an estimation that we thought by adding up all of these individual fractions it would add up to basically 1 full Post-it again? This formula confirms it. We just had to take the liberty of making an assumption here that this yellow piece was, for all intents and purposes, 0. That whole yellow piece really couldn't be done. So I was taking a bit of mathematical liberty and not officially calculating that yellow piece, but making an assumption. A safe assumption, but it was an assumption. And that's why we never used the formula. I mean, many of us probably wouldn't intuitively have done that, because why would you think about 1/2 to the power of infinity? But it can be done if you understand what's happening. And more importantly, that means this formula can be used. So the question now is, if the formula can be used, would it work for any situation? Or does it only happen to work for this single Post-it that we tried? We tried another Post-it problem. We tried it with 1/3. Let's see if the formula would work for 1/3. Let's see if it actually does make sense. To recap, we suspected that 1/3 plus 1/9 plus 1/27 and so on and so forth would give us about half of a Post-it as our answer. It would add up to about half, or 0.499999 something, and that's an estimation that I'm hoping my formula can give me. So let's see if that is indeed true. If I want to use the formula, I'd have a sub 1 is the first term. Now in this problem, the first term I tried to add was 1/3. I'd need a multiplier. Now, because I was taking 1/3, I'm effectively multiplying 1/3 for each subsequent fraction. So the multiplier is 1/3. And n is, again, an infinite series of fractions. I don't know how many fractions I'm supposed to add up, so I'll use infinity again. And now I'll plug into the formula and once again see if the formula works. The formula would be a sub 1, that's 1/3, times 1 minus r, that's 1/3, to the power of n, infinity, all over 1 minus r again. Now, let's use a bit of logic. 1/3 to the power of infinity. That's 1/3 times 1/3 times 1/3 times 1/3 times 1/3 times 1/3. Haven't we already talked about that? The fact that if you keep doing a third of a third of a third of a third of a third, it's going to get ridiculously small. We can verify with our calculator to make sure we're on the right track. 1/3 to the power of something big. Let's say 5,000. Yep. Even our calculator's like, nah, I can't do that. It's just 0. We know it's not 0. We know our calculator just ran out of digits, ran out of patience, but for all intents and purposes, we see that same thing happening again. I'll highlight it yellow just to reiterate it's the same situation. It looks like that big old goose egg is once again a 0. So if mathematically then I have 1/3 times 1 minus this big fat 0 from the fraction that gets so small I don't even bother, and then on the bottom 1 minus 1/3, then it looks like this is math I can do. 1/3 times 1 minus 0 is just 1. So 1/3 times 1 on the top is 1/3. Over 1 minus 1/3 is 2/3. Those don't cancel. So I will try to do a bit of a keep, change, flip sort of thing. 1/3 times the reciprocal 3/2. Conveniently, the 3's do cancel, which is cool. And then I'm left with, hey, look at that, 1/2. Remember how when we were looking at our Post-it, we sort of estimated that the cut up pieces that we were trying to reassemble back together looked like they added up to about half of a full Post-it? Well, this formula confirms it. All of those fractions, 1/3, 1/9, 1/27, 1/81, and even all the parts that I couldn't even do because they were so tiny, really do add up to 1/2. And, blessedly, it looks like I don't have to put my risk or my health at risk to be able to cut up all these individual fractions. I can use the formula and forget this scissors situation, and I can figure out what this answer is going to be without having to cut them apart, without having to individually add 1/3 plus 1/9 plus 1/27, which seems impossible, without having to cut, which again seems impossible, dexterity not included. So now that I have a formula that I can reliably use, let's just make sure it's clear. The formula itself is actually relatively user-friendly, but it's that 0 thing that still might cause some confusion. Going forward, I don't want that yellow part, that goose egg, to be confusing to the point where we wouldn't use it. So let's make a bit of an adjustment. That if we have an infinite geometric series, we're making the observation now that the same thing keeps happening. That when I have an infinite geometric series, this r to the power of n part to the formula really just ends up being 0 every single time. So r to the power of n always ends up being 0. And if that's the case, and I'll switch gears so I can do a bit more of a permanent proof here. If r to the n is always roughly 0, and I make that assumption, then the formula can evolve a little bit. 1 minus 0 is just 1. And 1 minus r on the bottom means that my formula has evolved to the point where I'd have a sub 1, whatever that is, times 1, which is just going to be whatever a sub 1 was, over 1 minus r. And that can be considered the formula for the infinite series. The finite series, where n actually stops at a definitive stopping point, I would definitely still keep using the original version of the formula. But for an infinite series, where n just goes on and on and on and on forever, and it's just going to end up giving us that weird goose egg again, I'm not going to use this version of the formula. I don't feel like this version is helpful, so I'm going to use the new and improved version of the formula. A sub 1 without the bothering of the r to the n part over 1 minus r. So to summarize, the formula for an infinite geometric series, and I'm writing this on a separate sheet of paper, which I'll explain in a second. The formula for an infinite geometric series is a sub 1 on its own over 1 minus r. It's a modification of the original formula for a geometric series. So, to summarize, you now have 2 geometric series formulas. And this is where I want to take a moment to just quickly make sure that I don't confuse anything. Take a quick look back, if you've written some notes, at the original formula that we wrote for the geometric series. Remember the original formula that we were using with the r to the n? Perhaps consider making a note to yourself next to the title of that formula that this is for a finite geometric series. A finite geometric series is when you have an actual value of n, an actual number of terms, like 8 terms, 10 terms, 13 terms, when the question tells you how many terms that you need to use. When you have an infinite geometric series, in other words, if you have a problem that goes on forever with the little ... that's when you use this modified version of the formula. So finite is when you have a set number of terms. Infinite is when the series goes on forever. And knowing the difference between them is definitely going to be important. I would recommend, if you haven't already, adding the infinite geometric series formula to your notes, so that way all of your notes are in one place. Because you'll be able to use your notes on any sort of assessment or quick check or warm-up, having them all in one spot is probably just going to make life easier, so that way you don't have to go searching around for all these different pages and all these different sources. But the idea now is that we can use a formula. We don't have to cut up pieces of paper. We don't even have to hardly use a calculator. We can find the sum of a geometric series simply by using the formula in its new and improved format. So in the next video, we're going to try to do a few problems in question number 6 that involve that modified formula. Take some time between now and the next video to make sense of the new formula and to make sure you understand what's going on, so that when we do the actual sample problems, you'll have a better sense of what we're doing and why.